Alright, welcome to Chapter 10 and 11 video for physics class. We're actually going to skip 10.2, so this video will cover 10.1 plus all of 11. I've kind of rearranged the order of the stuff, so it's not going to go linearly 10.1, then 11.1, then 11.2, but by the end of the video we'll have covered everything that's in these chapters, and it's all about energy and the different forms of energy, and how we can use that to help us solve problems. Alright, before we start talking about energy, we have to talk about the way that energy is transferred between two systems. Well, we don't have to, but it's nice to talk about the way that energy is transferred between two systems, so that when one gains it, the other loses it. And the way that we can do that is by this word work. So, in the previous chapter, we learned how if you multiply force times time, you'll get an impulse on something, and that will change its momentum. So we're going to do something mathematically similar in this chapter, but instead of multiplying force times time, we're now going to multiply force times distance, but the math will go along in similar fashion. So, because distance is a vector, when you look at son of a gun, because force is a vector and distance is also a vector, when you multiply the two together, you have to worry about which direction those vectors are pointing. Just like when you're adding vectors, you can only add them up normally if they're pointing the same way. But if they're at an angle to each other, you have to use Pythagorean theorem to add them. Likewise, when you're multiplying them, you have to consider what is the angle between these two vectors. And if they're not pointing the same way, then you can't just multiply the numbers. So the way that we do that, if you remember from pre-calculus, if you've had that, the dot product of two vectors finds the component of one vector along the other vector. So it basically tells how much they're aligned with each other. If they're perfectly aligned with each other, then the dot product will be maximized. And if they're perpendicular to each other, the dot product will be 0. And the formula for dot product was the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. So you need to draw in your object, which way it's moving, and which way the force is being applied. And then you can find out the work done by that force. So you might ask, well, how is it going to be moving a different direction than the direction of the force? Could be something like a sliding glass door that's constrained to move along the rails, or a train that's constrained to move along the tracks, but it's being pulled a little bit off axis. It will still move along those tracks even though the force is directed in a slightly angular direction. The units of work are going to be joules. If you multiply force times distance, you get newtons times meters, and newton times a meter. Even though you've seen that, no, have we seen that before? I don't recall if we've seen that before in torque, sorry. Even though you've seen that before with torque you leave it as newton meters, but with energy, or work, you're going to change that to joules. I mean, it's mathematically the same, but then the standard way to write it is joules, or capital J. Okay, so that's the definition of work. The next one is simple, the definition of power. Power is how fast work is being done, or how fast energy is being transferred. So you just divide how much work is done by how much time it took. So if you do a certain amount of work, which is force times distance, so either you apply a really big force or you go over a longer distance, if you do that more quickly, then you're going to be more powerful, or more power is being used. So the units are work divided by time. Well, work, we just said, was joules. Divided by time is seconds. So joules per second is a watt. And I'm sure you've heard of watts before when you're talking about light bulbs, like a 60-watt light bulb, or many other devices. How many watts they use, that's how much power is being consumed. And it's inversely proportional to time. The shorter the amount of time, the more power. Alright, work and power example, just kind of opening up those formulas as simple as possible. How much work is done when you open a sliding glass door by pushing 120 newtons at 10-degree angle from the glass? So suppose here's our railing, and here's our glass door. And the glass door is going to move this way, so this is the direction it's moving. And we apply a force of 120 newtons at a 10-degree angle. So we're actually applying a force of 120 newtons. So you want to set up a picture like this, it'll really help you. And the distance moved is 1.2 meters. And the angle here is 10 degrees. So if you get a little picture like this, it should be very straightforward to use the equation work equals force times distance times cosine of the angle. And this angle always is between this force vector and the motion vector. Okay, so the force is 120 newtons, the distance is 1.2, and you've got cosine of 10 degrees. And I hope by now you're getting used to me being a slacker and not having a calculator. However, wait for it, I have a calculator this time. So we'll type it in real quick, 120 times 1.2 times cosine of 10, and I got 141.8. So this was 141.8, and the units are going to be joules because it's work done. And so let's check first to see if this is reasonable. Like maybe your calculator's in the wrong mode or something like that. So 120 times 1.2, 12 times 12 is 144. So this should be around 144 if the two force and motion were perfectly aligned with each other. However, we're 10 degrees off, but 10 degrees is not very much. They're still mostly aligned, so the value we get here is still mostly the full value of 144, so it seems reasonable. That's how much work you've done. All right. How much power is consumed by a jackhammer if it exerts a force of 15,000 newtons over a distance of 5 centimeters and it hammers 10 times per second? Okay, so the formula for power we just said was work over time. Okay, well a jackhammer is perpendicularly applying a force right in the direction of the motion. So this is going to be work is force times distance cos theta, but we're going to assume here theta equals 0, and that's not explicitly stated in the problem, but frequently if the force is being applied directly onto something, it's in the same direction that the object is moving, because it's on a jackhammer, that's what's hitting the ground. So this is often the case even if it's not stated. Anyway, over time. Okay, so we have to figure out the force that's given, 15,000 newtons. Distance, 5 centimeters. We should probably convert that, right? So it's nice to set up your variables. You can be lazy and not do that, but frequently if you write them down, it will save you from making a mistake. So this is 0.05 meters because we have to convert what's given is 5 centimeters and we wanted it in meters. And lastly, the time. If they tell us it happens 10 times per second, then how long is it going to last for one cycle of the jackhammer? It's only going to be 1/10 of a second, which is 0.1 seconds. Okay, so converting from the information that's given into the variables that we need before we plug in. And now we can plug in 15,000 times 0.05 divided by 0.1. Okay, we'll type this in the calculator real quick. 15,000 times 0.05 divided by 0.1, 7,500. And the units are, the top is work, which is joules, and the denominator is seconds. So joules per second are watts. So that's quite a bit of power. I mean, if you think about a 60-watt light bulb, that's only 60 watts. So this is way more than that, which makes sense because a jackhammer is going to use a lot of energy. It's going to develop a lot of power. Otherwise, it's not going to be able to do anything. Okay, so those are your basic definitions of work and power. Now we'll talk about how doing work on something affects a change in it. So this is a little bit of math. Don't worry too much. I'll go through it quickly. The force of A on B is equal and opposite to B on A. Same thing we said with momentum. So when you multiply both sides of that equation by distance, these two sides of the equation are still equal. Okay, so the work done, when you multiply by distance, you get the work of A on B is the negative of the work of B on A. So that means if one thing does work, it's going to lose something, and the other thing is going to gain something. Back when we were talking about impulse, we named that quantity that was gained or lost momentum, but now it's something different because instead of multiplying by time, we are multiplying by distance. So this new quantity, this new something or other that's being transferred, we give a name for it, and we call it kinetic energy. Okay, so let's rearrange a little bit mathematically to get the formula. Back in chapter 3, we had this formula relating acceleration and distance to the initial and final velocity, because when something is going to accelerate, we know it's going to change speed. So if we include that formula with F net equals ma, rearranged for A, you can solve these two simultaneously or plug one into the other, and you get that the work equals 1/2 mv final squared minus 1/2 mv initial squared. Okay, so what's kind of cool about that is you have some final value of this quantity, 1/2 mv squared, and you have some initial value of this quantity, 1/2 mv squared, And if you subtract them, that's how much work is done. So whatever it is that's being transferred is whatever this quantity is, 1/2 mv squared. So we have to give we don't have to, but it's nice to give a name to it. So that quantity, 1/2 mv squared, is called kinetic energy. And we'll talk about kinetic energy a lot more in a couple of slides. But the idea is, when you do work on something, if you apply a force over some distance, you give it kinetic energy. You transfer kinetic energy to it, or take some away from it if your force is opposing it. So the mass typically does not change, but the velocity does change. So if you know how much force you applied and you know over what distance you were applying that force, you can figure out how much the energy changed. So it's a nice little analogy between Chapter 9 and Chapter 10. Work is a way to transfer energy. Impulse is a way to transfer momentum. Okay? But since a force does both of these things, you can't just look at one and not the other. Both energy and momentum are going to be transferred. If one is transferred, the other is also going to be transferred. And you can use both the equations in the same problem, and then therefore you can have more robust solutions. Alright, so just like we talked about conservation of momentum in Chapter 9, we can now talk about conservation of energy in Chapter 10 and 11. So because when it's transferred, one object gains it and the other object loses it in equal proportions, the total amount of all the objects combined at the beginning will equal the total amount of all the objects combined at the end. So this right here is a very, very, very important formula. And what goes into E total initial and E total final is what's going to be coming up in the next couple of slides and in the next two chapters. Alright, so the book defines energy as the ability to produce change in itself or the world around it. It's cool to think of it that way. It's hard to kind of actually describe what energy is, but when we go through each of the types that we're learning about, we'll try to see how it relates back to this definition of the ability to produce change in itself or the world. Okay, so what kinds of energy are there? Kinetic energy is the first one. We already mentioned that because that's what is being transferred when you apply a force to something and you do work on it. So kinetic energy is the energy of motion. The reason it's called the energy of motion is because it depends on the velocity. The faster an object is going, the more kinetic energy it has. It also depends on the mass. So at a given speed, a bigger object will have more kinetic energy. So mathematically, we can see the formula. Now we can conceptualize it as well. When something does work on you, it applies a force to you. So the more energy it has, the more work it was doing when it hits you, or the more work it took to get it up to that speed. So conceptually, getting hit with a ball that's going faster is going to hurt more, or getting hit with a bigger ball is going to hurt more. And now let's also think about this. Does the direction matter? Okay, this is velocity squared. So even if you plug in a negative number, you're going to get out a positive number. So the direction does not matter anymore. So kinetic energy is not a vector, it's just a number. So let me even write that. Not a vector. So kinetic energy does not have an associated direction. It's just a numerical value. So if you gain some, the value goes up. If you lose some, the value goes down. But left and right are not included at all. So the last really, really important thing about kinetic energy is that in order to tell whether or not you have kinetic energy present in your problem, what you need to do is you need to ask yourself, do I have objects in my problem that have velocity? If there's anything in your problem that has velocity, then there must be kinetic energy involved somehow. Now, if the velocity is staying constant, then the kinetic energy is not changing. But if the velocity is changing, then the kinetic energy will be changing. So this is called an indicator, and we're going to talk a lot about indicators because when you're setting up a problem, you have to ask yourself about each of the different types of energy to see whether or not you need to worry about it. And so the way that you do that is you ask yourself this question: is the indicator present? So is velocity present in any of my objects? And if it is, then you include that kind of energy. Okay, so kinetic energy, summarize, energy of motion, formula 1/2 mv squared. Very, very important. You need to write this down, memorize. Okay. Another classification of energy, instead of the energy of motion, is called potential energy. And potential energy, it depends on the internal characteristics of the object. So it depends on the position of the object or the shape of the object. But it doesn't matter if the object is moving or how fast it's going. So there's lots of different internal properties of objects, and therefore there's going to be more than one type of potential energy, and we'll go through those next. The last thing about potential energies in general is we need to have some kind of reference point. Otherwise, well, you'll see soon enough that if we don't have a reference point, you could arbitrarily say that some certain object has an infinite amount of energy or no energy. Because you're measuring something about its position, you have to see how its position has changed from one point to another point. You can't just look at the object in its overall position state. But this will become very clear in the next slide, so let's just zoom right ahead. Okay, potential energy of gravity. The higher an object is, the more energy it has. So this is why you need a reference point. If you say that the bottom of the hill is your 0 point, okay, well, it's messy, but there's a 0 point, then the top of the hill has some height, and therefore this car has some amount of potential energy based on the fact that it's up here at some height. And it has the potential. Remember we said the definition of work is the ability to cause change in itself or the world around it. Well, if this car slides down the hill, it's causing a change in itself, it's speeding up, and then if it hits something, it's going to do damage to it, so it's causing change in the world around it, or it has the potential to do that. But again, you could define the 0 point as something like, what if you defined 0 as right here? Okay, then arguably this car right here has 0 energy. Okay, does that mean it suddenly can't have the potential to affect the world around it? Of course not. Because if it still goes from here down to here, there's still a change in energy associated with that. So we don't necessarily care about the numerical value of the energy at this point or the numerical value of the energy at this point. What we really care about is the change in energy from one point to another. So if I go from 0 down to like -10, that's the same change in energy as if I call this 10 and I call this 0. So from 10 down to 0, or from 0 down to -10, they both have the same change in energy, and therefore they both have the same effect on the world around them. So you can choose your 0 point, just like back when we were doing origins and positions, you can choose your 0 point to be anywhere for the excuse me. You can choose your position to be anywhere for the height, as long as you're consistent and you measure the change. So your formula here, remember, work is force times distance. And what force is it? When you lift something higher up into the air, what force are you overcoming? You're overcoming the force of gravity. And so if you multiply the force of gravity times how high you lift it, that will tell you how much energy the object has, or how much work you've done, which tells you how much energy the object has gained. So potential energy of gravity is mg delta h. So the potential energy of gravity, and notice there's a delta right here. So we care about the energy changes, and the energy changes when the height changes. So mgh is potential energy of gravity, and we look at the delta in the delta. So if your object is changing height, then you know there's going to be a change in the gravitational potential energy. Alright, next one. Oh, here's a quick example, dropping a ball. We previously studied dropping a ball in terms of the forces on the ball, but now we can look at it in terms of kinetic energy and potential energy. So as a ball falls, what happens to its height? Well, the height decreases. What happens to its potential energy of gravity? Well, that's going to decrease because the height is decreasing. But as the ball falls, what happens to its velocity? The velocity is going up. Therefore, what happens to its kinetic energy? The kinetic energy is going up. Okay, so as the height changes, what's going on is that you're starting off with potential energy, and it's being converted into kinetic energy so that the overall total energy stays the same. It just changes type. It just changes type from one type to another. So it's kind of like, if I like thinking about energy as money, and you might start off with like $100, and then you can convert that into euros or something. You still have the same amount of money even though you've changed what its type is. And you have to ignore the fact that the exchange ratio changes. Pretend the exchange ratio is always the same, because energy is conserved always. Alright, third type and the final type for this lecture and this chapters is spring potential energy. So potential energy, we said, depends on the shape and location of the object. So gravitational potential energy was dealing with the location of the object. How high is it relative to some ground level reference point? Spring energy deals with the internal structure and the internal shape of the object. So if you stretch something out or you compress something, you had to apply a force to do that, and therefore there was a force applied over some distance as you compressed or stretched it. And so you did work on it, which means it's storing energy. Okay, so there's a formula here for the force exerted on a spring. you should know this one. Even though it's not an energy, it's very closely related to the energy. So to compress or stretch out a spring, you have to apply a force that's K times X. So K is the spring constant. The higher the value of K, the stiffer the spring is and the harder it is to compress. And then X here is the distance that you stretch it from its equilibrium position. So you take a spring, you set it down with no forces on it, and you see how long is it. And then you stretch or compress it a certain distance from that equilibrium position. And that's what you're plugging in here. It's the length stretched or compressed from equilibrium, not the actual length of the spring. Okay, because when it's in equilibrium, you don't have to apply any force at all, but it still has some length. Alright, so when you stretch or compress, we just said, you applied a force over some distance, therefore you did work. So the spring has energy now. So the formula for spring energy is 1/2 kx squared. 1/2 kx squared. And we're looking at the changes in energy from the initial to the final. So we put a delta here and we put a delta here. So basically 1/2 kx squared final minus 1/2 kx squared initial. Kind of like kinetic energy. Similar formula, 1/2 times some constant times the variable squared. So how can you tell if you have to worry about spring energy? Well, obviously, if you have a spring that's stretching or compressing, then you're going to worry about spring energy. That could also be things like a bow and arrow, like the drawstring on a bow and arrow. That's a spring that's being stretched out. Slinkies are examples. Anything like that. Shocks in a car are examples of spring energy. Alright, so a couple of quick examples, and we're moving right along. If your 2100 kilogram car has 400,000 joules of kinetic energy, as you drive down the road, how fast is the car going? So kinetic energy, our formula, is 1/2 mv squared. The question is, how fast is the car going? So before plugging in the numbers, we should probably solve for the velocity, yeah? So multiply both sides by 2. Cool, that's gone. Now divide both sides by m. Divide by m. So now I've just got v squared by itself, so I need to take the square root. So my velocity is the square root of all that. So algebraically, you can go from here to here, and you should be able to do that in a couple of steps on your own on a piece of paper. Now we can plug in our numbers. 2 times the kinetic energy, 400,000 divided by the mass, which is 2100. Take the square root. Whip out your handy dandy calculator. Clear 2 times 400,000 divided by 2100. Raise it to the 0.5 power, and I get 19.5. Oh my goodness, what are my units? Well, if I put in kilograms and joules, those are SI units, so I'm going to get out SI units, which are meters per second. But the question is, how fast am I going in miles per hour? Alas, we need to learn how to convert, or remember how to convert, since we already learned. So 19.5 meters per second. I'm going to need a couple of conversion factors. I'm going to need to know that 1,609 kilometers are in 1 mile. And I'm also going to need to know that 3,600 seconds are in 1 hour. Okay, so my seconds and my meters will cancel. I made a mistake. So seconds here, cancel the seconds here. I wrote 1,609 kilometers. That kilometer should not be there. 1,609 meters is in 1 mile. So my meters cancels with my meters. So my final answer here, 19.5 times 3,600 divided by 1609, 43.6 miles per hour. So 43.6 miles per hour is a pretty reasonable speed. You're cruising down the road. Your car has around 400,000 joules of kinetic energy, which explains why when cars hit things, they do a tremendous amount of damage. That is a large amount of energy. And you'll compare it to the values coming up in the next two problems just to see how big it is. Okay, next example. When you kicker kicks, well, when a kicker kicks a 1.2 kilogram football for a field goal, it reaches a max height of 15 meters. So it's going to go up and come down, and that right there is 15 meters. Okay, how much potential energy of gravity does it have? Okay, so potential energy of gravity is mgh, and I've put this little reminder in. Does your reference point matter? Absolutely. I could just choose my value right here to be h equals 0, and then how much energy does it have? Well, it has 0. But I mean, that's kind of a cop-out, right? We kind of want to know, most likely we want to do the energy relative to the ground. Okay, so that's not a good choice. Let's choose h equals 0 to be on the ground, so that when it reaches its highest point, that's 15 meters up. Okay, so now we go 1.2 is the mass, g is 9.8, and the height is 15. So the potential energy of gravity, we should put a little subscript g right there, is 1.2 times 9.8 times 15. 1.2 times 9.8 times 15. 176 joules. 176 joules. So you can see, compared to the car, this is a really, really small value, which makes sense. It's just a small little football. So it hits you, it's got 176 joules. It doesn't have as much potential to cause enough change in the world around it. So remember, energy is the ability to do change on yourself or the world around it. A football has 176 joules of potential to do work or change in the world around it, whereas your car had what? 400,000 joules worth of ability to cause change. So big difference. Okay, last one, a pogo stick. Very cool. A pogo stick has a spring that compresses as you jump. Makes sense. Suppose the spring compresses 12 centimeters, then stores up all the energy that you had as kinetic energy. So as you're falling down onto it, you're moving, so you have kinetic energy. That's being stored in the spring. Suppose it's 40 joules. What's the spring constant in the pogo stick? Okay, well, the potential energy in a spring is 1/2 kx squared. Okay, so it compresses 12 centimeters, so that means x is 12 centimeters, which we must immediately convert to 0.12 meters. Okay, potential energy, I mean to make a label here, spring, is 40 joules, which is a very small amount, of course, and the constant is what we're trying to find, yeah? So we should algebraically solve this first. Notice the symmetry between this equation and the kinetic energy equation. To solve for k, we'll multiply by 2. So k equals 2 times potential energy in the spring, and then we have to divide by x squared to get the k by itself. Now we can plug in our numbers. 2 times 40 divided by 0.12 squared. Okay, calculator. 80 divided by 0.12 squared is 5,555.5 repeating. So let's just call it 5560 newtons per meter. The units here are newtons per meter. It's maybe not that easy to see that it's going to be newtons per meter, so let me show you briefly. The units here is joules, and in the denominator it's meters squared. Okay, but joules is force times distance, so that's newtons times meters over meters squared. So one of these will cancel with one of these, leaving you with newtons per meter. Okay, so the spring constant is 5,560 newtons per meter. What that means is, to stretch out this spring, or to compress this spring, by a distance of 1 meter, it's going to take a force of 5,560 newtons. So you might think, well, that's a lot of force, but 1 meter is a really long distance. I mean, if the entire spring is only this long, to stretch it out 1 meter, that's a really, really long distance. The spring is probably not made to stretch that far, so it's going to take a huge force. So, when you jump on a pogo stick, it's only compressing like this much. So the full weight of your body is only compressing it this much. It's going to be a pretty stiff spring. So a spring constant in the thousands is a reasonable value for that. Okay, so far we've seen kinetic energy is the energy of motion. You're looking at velocity as your indicator. We've seen potential energy of gravity, where you're looking at how high the object is. And then we've seen potential energy of springs, where we're looking at how much the spring is compressed or stretched. Okay, so each one by itself, not so bad. Simple formulas for all three of them. So what happens if you've got energy being converted from one form to the other, and we think of this idea that, well, what if energy is lost? So earlier we just said energy is conserved, so it can't be lost. But you see things all around you where they slow down and stop. Or you see a pendulum swinging, and over time it doesn't swing quite as high. So what's happening? Where's that energy going? So the energy is not actually lost, but it is converted via work to other forms, specifically thermal energy. Okay, so when you have friction or air resistance in your system, that is a force over some distance. So work is being done there, and that energy is being converted to thermal energy, which is a whole new type of energy that we're not going to learn about just yet, but that's the basis of a large portion of Chapter 12. So for now we'll say the energy is, quote, lost, but in the back of our mind we're remembering it's not actually gone, it just moved into a different form. Okay? When you have collisions, so this is now more of like the complex problems and where the math is going to come in. When you have collisions between objects, momentum is always conserved. This you have to remember. Even though we've moved on from the chapter on momentum, you're still going to use the equation for momentum frequently. Momentum is always conserved, so P initial equals P final, but the kinetic energy is only sometimes conserved. Total energy is conserved, but specifically kinetic energy is not always conserved because some of that kinetic energy could be converted to other forms, aka lost, but what we really mean is converted. So there's two names for collisions. An elastic collision means that the initial and final kinetic energies are the same. So maybe you have two rubber balls and they bounce off each other. Okay, in that case, pretty much no energy is lost, and the total kinetic energy at the end will equal the total kinetic energy at the beginning. So you can set up an equation, Ke initial equals Ke final. But in a lot of collisions, energy is lost to thermal energy or sound or light or other types of energy, and those are called inelastic, so not elastic. Basically, elastic is bouncy, right? And then inelastic is not bouncy, so a lot of times they stick together. So say you have a car crash and the two cars crash and the bumpers stick together and then they move off in some direction. Well, that took a lot of force over some distance, therefore energy, to bend the metal, and therefore there's going to be energy lost. Okay, last slide, complex examples. In your problems, you're more than likely going to have different variables and different types of energy interacting together at the same time. It won't just be one problem only about kinetic and then one problem only about potential. These energy types are interchanging on a regular basis. So the setup for these problems is going to be very similar to momentum. First, you want to draw a picture of the before and the after, because your variables will be changing, how fast things were going, how high they were, and how much they were stretched or compressed at the beginning, and then those same variables at the end. Label everything that you know, and then label question marks for the things you're trying to find, and set energy initial total equal to energy total final. So within energy initial, you can have different types, right? So far, you can have the kinetic energy initial, plus you can have the potential energy of gravity initial, plus you can have the potential energy of springs initial. So you can have up to 3 things here on the left-hand side, and then you can have those same 3 things, 1, 2, 3, on the right-hand side. So all the initial values here, all the final values here for all 3 of those. Now, maybe you have nothing that's stretching or compressing. Then you don't need to include the potential energy of the spring before and after. So in general, you can have up to 3, but you won't always have all 3. And the way that you see which ones to include is by checking the indicators. Remember what the indicators are. For kinetic energy, it's things moving. For potential energy of gravity, it's how high things are. And for springs, it's how much they're stretched or compressed. Finally, you can solve for the unknown variables in this bigger equation. And maybe you have 2 unknowns, then you need to bring in a secondary equation such as P initial equals P final. Okay, complex examples. So this is our last 2 examples before the end of the lecture. A 5,000 kilogram tractor drags a plow through a field at a constant speed of 2 meters per second. The tractor must overcome a 60,000 Newton friction force. How much kinetic energy does the tractor have? Well, this is actually a pretty easy question, not that complex after all, because the formula for kinetic energy is 1/2 mv squared. Do we know the mass? Yes. Do we know the velocity? Yes. So 1/2 5,000 2 squared. That's pretty simple. That's 10,000 joules. Okay. How much power is the tractor engine producing? This is a bit trickier. How much power? Well, the power is the work over time, okay? Well, work is force times distance, over time. Okay, well, distance over time is what? Distance over time is your velocity. This is kind of cool. So the power, another way to write the power is actually force times velocity. Right? If you're applying a force on something, the faster you're going, right, the more distance you're going to cover. So it seems reasonable. The force then is 60,000. And the velocity is 2 meters per second. I guess I should put in here newtons. And so the power that you're exerting is 60,000 times 2, which is 120,000 watts. And you can just put a capital W. I like to write it out sometimes, watts. So a newton times a meter is a joule, and a joule per second is a watt. So this tractor is putting out a ton of power, and that seems reasonable considering it's got a huge friction force to overcome because it's dragging a plow through a field, right? I mean, the whole point is that you're tilling up the ground and rocks and roots and stuff from previous crops. So it's going to take a lot of work, therefore it's going to take a lot of power to do that. Okay, so this is an alternate formulation for power, force times velocity. Okay, a 2 kilogram ball is shot straight up at a speed of 20 meters per second. How high does it go? Okay, you could solve this problem using the projectile motion equations, but now I want to show you a much easier way to do it. Okay, you shoot the ball straight up and say up here. So here the velocity is 0. Here the velocity was 20. Okay, here the height was 0. And here the height is something that we're trying to find. So what types of energies do we have in this problem? We've got kinetic energy because it's changing speed as it goes up, and we've got potential energy because it's changing height, but we don't have any springs, so we don't have to worry about that. Okay, so we can say that energy initial equals energy final. Well, at the beginning, what type does it have? When it's down here, it doesn't have any height, so it has no potential energy, but it does have speed, so it does have kinetic energy, 1/2 mv squared. Okay, at the end it has no speed, so it has no kinetic energy, but it does have height, and so it's going to have potential energy. And now we can solve this to see how high it goes. Well, m cancels out, m cancels out. We can divide by g, okay, g cancels out, and we're already left with the height. The height is velocity squared over 2g. How simple was that? Very cool. So velocity squared is 20 squared, and that's going to be 400 divided by 2g. G is roughly 10, so 400 divided by around 20 is around 20 meters high. A little bit more. You can type in your calculator if you want. But you can see that this is probably a lot simpler way to do it. You don't have to figure out how long it takes to get up there and then plug into these chapter 3 equations. So as long as you're not worried about how long it takes, using energy to solve these problems has a huge advantage in that you can solve it in one step. Suppose the ball lands perfectly on a trampoline with spring constant 1200 newtons per meter. How far does the trampoline compress? Neglect and then include the minor change in height. So the ball, say now we're starting, the ball's up here, and it falls down onto a trampoline, and the trampoline is going to compress a little bit, some distance there, right? So the energy at the beginning is the potential energy of gravity, and the energy at the end, if it falls back down to the ground, is going to be the potential energy stored in that trampoline spring. Okay, so we can set these two equal to each other. So potential energy of gravity is mgh equals 1/2 kx squared. So how much energy did it have at the beginning? mgh we know. Oh, we don't know the mass. That's curious. Oh, we do. 2 kilograms. So 2 kilograms. Gravity times height. Well, gravity times height we just said is actually, well, I'll just put it in. 9.8 times height, which we said was around 20. So this whole product here, should be, what, 400? Yeah, 400. Because this value was not quite 20. There's a little bit more than 20. Again, coming from right there. Equals 1/2 kx squared. So times both sides by 2. I'm being a bad teacher. I'm being a really bad teacher. Let me back up. I'll just put it in 1/2. K is 1200. And we've got x squared. Okay, so multiply both sides by 2. That gives us an 800 here. Divide both sides by 1200. And that equals x squared. And, okay, 8 over 12 is 2/3. Take the square root of that, and you get the square root of 2/3 as your distance that this will stretch. The square root of 2/3 is, wait for it, 2/3 to the 0.5 power, 0.82. 0.82. So what that means is the object started off with kinetic energy, goes up into the air. Kinetic energy is changed into potential energy, so at the very, very top it has all potential energy. As it falls back down, that potential is converted back into kinetic, and then when it hits the trampoline applies a force to it, which slows it down, decreasing its kinetic energy, but that causes the trampoline to stretch out, which increases the stored spring energy in the trampoline, and it would stretch out about 0.82 meters. Okay, so that's neglecting the change in height of the trampoline itself. But then you have to ask yourself, wait a minute, if the trampoline stretched down 0.82 meters, then that was another change in height. So the change in height was not exactly whatever this 20 meters was. It's actually a little bit more than that. So how do we take that into consideration? And I think actually, just because this video is getting long, I'm going to skip it for now. But I encourage you to try to figure it out. You're going to have to label this value here x, and this value here is your height. So the change in height is h plus x. You'll have some variables on both sides of the equation, and the math gets a little bit more fun. And we might take a look at this in class. Okay, congratulations, you finished both chapters 10 and 11. Well done. We'll talk about the homework, but it's going to be probably combined into one larger assignment over a couple of weeks. Good luck. I look forward to talking about this in class. And don't forget to fill out the forms.